when it comes to Haber process, okay, Haber process, by now you should know that Haber process is going to be a process to produce ammonia. Okay, so if we look at the process of a Haber process, it's going to be a reversible reaction. Therefore, we need the nitrogen, okay, reacting with hydrogen to give you ammonia. So if we balance this equation, it's going to be something like this. Okay. So we need to know what are the things that we need to know about this Haber process. Is going to be obviously we need to know about the catalyst that is being used. Okay. The catalyst that is being used for Haber process is going to be iron powder, iron catalyst. Okay. So one of the important thing, okay, that we need to actually remember when it comes to this Haber process and contact process are going to be the conditions. The conditions covers the catalyst, okay, and also it also covers the temperature and pressure. So therefore, you need to actually memorize this, okay. So even in the textbook, I don't think so it's written, okay, the values are written, but when it comes to in your exam, okay, they will actually test you on this. Okay, you need to know what is the exact value for the temperature and pressure. Okay, so Haber process, they happen, okay, at the temperature of 400 to 450 degrees Celsius. Okay, you do not need to actually write 400 to 450 degrees Celsius in your exam. You can actually write it down as 400 or 450. It's up to you. Okay, so I'll leave it to you. And the pressure that is required for Haber process to happen, okay, the pressure is going to be 200 atmospheric pressure. Okay, 200 atmospheric pressure. So you need a very high pressure, okay, for Haber process to happen. Okay, so this is going to be, do remember all these conditions because we have learned about this equilibrium. All these conditions, these both conditions, they are comes under compromised condition. Okay, compromised condition. Okay, compromised temperature and pressure. Why? Because you should know, I think this one I'll just put down, delta H is going to be negative 92. Haber process is going to be an exothermic process. So we need to know that, like for example, if I use, okay, a high temperature, okay, because if we want the process to go to be shifted, okay, the position of the equilibrium to be shifted to the right, okay. So we know that this is going to be exothermic, so this is going to be hot, okay. So this is going to be cold. So if I use high temperature, okay, according to LCP, okay, Le principle, okay, Le principle, yeah. So when you look at the higher temperature, you need to bring down the temperature, okay. If you bring down the temperature, the position of the equilibrium is going to go to the left, okay, from hot to cold. Okay, we don't want the temperature to be too high. Okay, but when we look at this temperature is considered to be, I think generally when human beings, whenever we see anything that is more than 100 degrees Celsius, we think that that is already too high, temperature is too high. Okay, but actually 400 to 450 degrees Celsius, the temperature is not very high when it comes to industrial standards. Okay, so the temperature is still, in this case, is going to be a compromised temperature. Why? Because we know that if you use lower temperature, the reaction is going to be the forward reaction is going to be favored, or the exothermic reaction is going to be favored. Why we don't use 50 degrees Celsius instead of 450 degrees Celsius? You may ask me. Yeah, because of course, if you are using 50 degrees Celsius, you are going to get a lot of production of ammonia. Okay, a lot of production of ammonia. But the problem is you might be actually need to wait for the production maybe for 100 years. We don't want that to happen. Why? Because the rate of the reaction is going to be very, very slow. So therefore, we need to actually come into this what we call as compromise condition. The temperature must be is low, but it's not too low. So it's still a bit in the middle. Okay, if you want to put it like if it is too high, maybe it's about temperature 2000 degrees Celsius. So if you compare with that standard, okay, 450 is considered to be low. Yeah, but it's still a bit for our standard, it looks a little bit more than 100 degrees Celsius. Okay, the reason why they don't go to the extreme end, which is going to be 50 degrees or maybe room temperature, is because the reaction will take a lot of time. Because in Haber process is the production of ammonia at larger scale in industry. So whenever we are talking about industry, we want to produce something in a fast manner. We don't want to actually, it's not like an investment, wait for 10 years, 20 years, and you want to get and see the money. No, it's not like that. So whenever we want to produce something, yeah, within 1 or 2 days, or maybe in 1 week, we want to get things happening. Yeah, so that is actually the reason why. So the reason why they actually use this compromised temperature is because they want the reaction to be not too slow. Okay, they don't want the reaction to be too slow. So the reason not too slow. So you need to actually explain about this using LCP. Okay, why we use this compromise condition. And then for pressure, okay, do remember this is going to be gas, gas, and gas. And if you look at the total number of molecule over there, or the number of moles, you see 1 plus 3 is going to be 4, and then this is 2. Okay, so if I use 200 to our standard, please remember to our standard is going to be 1 atmospheric pressure is our normal atmospheric pressure. Okay, 200 is considered to be high pressure. So if you are using high pressure, according to LCP, you need to decrease the pressure. Okay, so when I decrease the pressure, you see that, okay, the position of the equilibrium is going to be from 4 to 2. Okay, you want to have less number of moles, okay, that is being formed. Okay, this is what we have learned in your equilibrium. So when this, in this case, it is favoring the forward reaction, which we are all happy. But okay, do remember, we do not, okay, according to industrial standard, 200 atmospheric pressure is nothing. Okay, because according to industrial standard, it can go to 1000, it can go to 2000. So we know that high pressure favors forward reaction. Why don't we use 1200 atmospheric pressure instead of 200? Okay, that will be the question. That is actually the
Due to
compromise condition. Okay, yeah, Kenneth, you were saying something. Why we don't use that?
Is it because it's too expensive?
Yeah, one is actually too expensive because in order to hold or withstand that pressure, okay, you need to build the infrastructure holding that container to be, maybe the thickness of the wall must be very, very thick so that it can actually withstand that pressure. So it's expensive. Okay, uh, okay, it's expensive. Or if let's say you still, some companies, even I think some companies, they still want to maximize profit. They say, oh, you need to build the wall maybe 1 meter thick. They want to save money. They say, okay, 1 meter thick. People will keep on saying this kind of things. We do according to our way. So they end up building 50 centimeter thick. So what happens, in order to save money in that sense, okay, they use high pressure. What happens, okay, the entire infrastructure explodes, okay, because cannot withstand that pressure. So that is going to be dangerous. Okay, so it's going to be dangerous because it can explode. Safety precaution. Okay, so if you want to put it, because of the safety reason, we don't actually use very high pressure. Okay, so these are the things when they say why why do we still use compromise condition? So I have discussed, I'm discussing this Haber process based on two perspectives. One, okay, based on rate of reaction. Okay, based on rate of reaction. Of course, if you want things to be fast, yeah, we still need to have the temperature to be high. We still need to have the pressure to be high. Okay, but we still need to look into equilibrium. Okay, your further your equilibrium part. So where under the equilibrium part, we need to still look at, okay, the position of the equilibrium. Okay, so in this case, the position of the equilibrium matters over here. So you still need to come into this what we call as a compromise condition. So these questions are very popular. Okay, which one, I repeat again, which one are very popular? They will ask you about the catalyst. They will ask you the value of the temperature. They will ask you the value of the pressure that is being used. And they will mention that this is going to be a compromised condition. What is the reason behind using this compromised condition? So to make sure that it's not too slow, if we use higher pressure, then it's going to be too expensive and it's going to explode. So it's a safety concern. So all this will matter. Okay, so this is one of the popular question. Yeah. Now, if we are talking about Haber process, we cannot forget about, okay, talking about contact process. Okay, so contact process, okay, is going to be a process that is going to be production of sulfuric acid in industry. Okay, so H2SO4 production. Now, what you need to know about this production of H2SO4, okay, they have few steps. Okay, and this one I don't expect you to actually learn about the steps immediately. Okay, but we will focus on one particular step. Okay, so I will write down all the steps first. It starts from sulfur, okay, plus with oxygen gives you SO2. Okay, it's a straightforward reaction. Okay, sulfur you oxidize, okay, with oxygen it give you SO2. But do remember, when you have SO2 plus oxygen, the reaction is not straightforward. It's a reversible reaction. And this reversible reaction, therefore, they will give you SO3. Okay, if you want to balance this, okay, I just put half over here. Okay, it's balanced. That's going to be the second step. Which step we are interested in? This step. Okay, this is the step that will involve catalyst. This is the step that involves the conditions. Okay, so I will proceed. Okay, once you have this SO3, what will happen? Now, this is going to be the funny part. In order to produce sulfuric acid in a massive scale in industry, you need sulfuric acid. Okay, you need sulfuric acid. So if you have SO3 plus H2SO4, this one small amount of sulfuric acid, okay, it will give you what we call as oleum. Okay, H2 sulfur, that's 2, so S2, O is 3 and 4, so O7. This is known as oleum. Okay, oleum is going to be produced. After that, okay, once you have oleum, you are going to have the fourth step, which is going to be H2S2O7. You are going to put water, it will react with water, and it will give you 2 moles of H2SO4. So this is the part. In order to produce sulfuric acid, you are using sulfuric acid, okay? But okay, do remember it's actually using small quantity of sulfuric acid to produce more, okay, in industry. So H2SO4. Now, what is important? I am going to focus on step number 2, okay, because that is the step that involves the catalyst. So I will actually extract that step over here. I will put it over here. SO2.
Sir,
Yes.
why can't we just dissolve sulfur trioxide immediately?
They dissolve the sulfuric trioxide immediately. They cannot do that
Hmm.
because the amount of sulfuric trioxide that is going to be produced from the step number 2 is too low. And then if you have that small amount of sulfuric trioxide, okay, when you dissolve with water, it's still going to be a reversible reaction. So it's still going to actually give you a small amount of sulfuric acid. So it's still not a complete reaction. So the production
So
is going to be quite less.
if it's dissolved in sulfuric acid first to make
Mhm.
oleum, then oleum is dissolved, it's more yield. It gives a better yield.
Um, like for example, you see it, the moment you get a SO3, okay, and you have the H2SO4, okay, you are going to get oleum. So this oleum, you can assume that this oleum is a very concentrated, in a very concentrated condition. And when you add water, and then you are going to get more sulfuric acid in a dilute condition. Yeah. But if you are using the SO3, okay, the amount is quite less. And then when you add with water, you are like further diluting the SO3, and you are going to get the H2SO4, which is going to be way lower. Okay, the yield that you are going to get is way lower. And again, do remember um, the reaction with SO3 plus H2O, they do not give you H2SO4 straight away. They do give you H2SO3 first. So I think there is a mixture of product that is going to be given. Okay, but again, we can actually look more detail about it. But according to contact process, okay, they do produce oleum first. Okay, they do produce oleum first, then they will proceed. So this one, if we want to look further, okay, let me actually check also, is there other reasons why they don't actually add the SO3 directly to water? Okay, if I find something else, then I will let you know also. Okay, is there any safety reasons? Okay, is there any other concerns? Is there like it will give you some kind of poisonous gas or something? Okay, so I will let you know. Okay, is it actually related to uh, safety concern? But again, generally, if you look at contact process in any books, it involves these four. Okay, it involves these four. And even I think the writing the oleum and so on, I don't think so is actually one of the focus in your syllabus. Okay, it's not one of the focus in your syllabus, because the focus in your syllabus is to look at the condition at position number 2. So the position number 2 is the one is being focused over here, because they do not want you, they will not ask you write down the steps to produce sulfuric acid. Okay, that is not in your syllabus. So I introduce to you only, yeah, because so that you can understand more how sulfuric acid is being formed. Okay, but okay, in this case, if I extract, okay, let's go back to the number 2. Yeah, if I extract this equation, the number 2, okay, do remember this is going to be the step that involves, okay, this one, do remember, is going to be addition of oxygen. So it's some kind of looks like oxidation, and it's like something like combustion. Therefore, okay, this enthalpy change is negative. But since it's not very popular, so I don't memorize what is the number. Okay, unlike for uh, ammonia, Haber process, I remember the number. I memorized the number 92, negative 92. Okay, but okay, for this one, I don't remember, but it's going to be negative. Definitely, it's going to be an exothermic reaction. Yeah, exothermic reaction. But okay, what we need to know is going to be the catalyst that is being used over here. The catalyst that we use over here, this is really important in your syllabus. Okay, it's going to be V2O5. Okay, it's called vanadium pentaoxide of vanadium 5 oxide. Okay, vanadium 5 oxide. And what is going to be the conditions, the temperature and the pressure? Okay, the temperature will follow the same thing like in Haber process. 400 to 450. But okay, for sulfuric acid, okay, the pressure is going to be 1 to 2 atmospheric pressure. It's different than okay the 200 atmospheric pressure, okay, for Haber process. Okay, so it's going to be lower, okay, or close to our normal temperature pressure. So do remember both of these are also compromised, okay, compromised condition. So let's actually analyze a little bit about them. Yeah. So if you analyze a little bit about them, okay, I think if you want to analyze about pressure, let's actually balance this properly. So this one will be 2, this is 1, so this one will be 2. So all of them are going to be gases. Okay, if let's say we are looking at the pressure, okay, 2 and 1 to 3, and this is 2. So in order to actually produce a lot of SO3, okay, should I use high pressure or low pressure? So in this case, it's kind of low pressure. So if I use low pressure, okay, what will happen? Low pressure is going to actually, according to LCP, it's going to increase the pressure. Okay, so if you increase the pressure, it's going to go towards here. Okay, so hold on, let me actually double check. Did I actually give the conditions correctly? Yeah, hold on. Yeah, the conditions are correct. So do remember, okay, so in this case, if I use, okay, if I use low pressure, okay, too low pressure is going to actually proceed, the reaction is going to be proceeded to the left, okay, to the left. So therefore, okay, the pressure must be a little bit higher, okay, but for this, okay, it's going to be slightly different because they didn't go up to 200. Okay, they didn't go up to 200, but in supposed to be, okay, if I want to actually explain, they you can explain in order to have more yield, okay, in order to have more yield, you need to use high pressure. Okay, you need to use high pressure. So if you use high pressure, the pressure will be low, then it's going to actually move towards to the right. Okay, so this is going to be according to LCP, but we cannot use according to LCP because, okay, uh, the safety reason. Okay, because of the safety reason, but it's slightly different for for the Haber process we use 200. Okay, but this one they use way lesser than that. Okay, so different compounds or different production, they have different values. So this one you just accept only lah. Okay, so they have mentioned that the pressure that is being used is about 2. Okay, so 2, you can use 2. So 2 is going to be compromised, and also the temperature that they use is 450. According to LCP, if you want to move to the right, this is going to be hot, that is going to be cold. So from cold to hot, okay, you need to actually use the lower temperature. If you use lower temperature, then the temperature should be increased, then they will move from cold to hot. Okay, so the temperature must be low in order to produce a lot of SO3, but the temperature that I use is not low. Okay, the temperature that I use is slightly higher. The reason, the same reason. If I use too low temperature too low, the reaction is going to become too slow. Okay, the reaction is going to be too slow. Why I don't use high pressure? Okay, why I end up using 2 atmospheric pressure only? So it's again related to cost. Okay, it related to safety. So the same reason that you have mentioned that we have discussed over here is going to be used over here as well. So it still doesn't matter. Okay, so these are the things that I really want you guys to actually understand for today. Okay, so contact process and Haber process. Yeah, So any questions up